In this video, I'll go over mathematical analysis of merge sort algorithm. You're familiar with merge sort and how it works basically. It's a recursive algorithm. You start with a list of size n, let's say, and then what you do, you split that list of size n into two sublists of size n over 2. You divide it in half and then apply merge sort recursively to those sublists of size n over 2. And of course, the sublists of n over 2, again, recursively you sort them, meaning that each of those sublists will split into two sublists of size n over 4, right? And this continues until you reach the base case of the algorithm, where you have single elements and then you start merging the elements. Now, with that in mind, what we do in mathematical analysis of recursive functions, what we do, we write a mathematical recursive equation that describes the recursive function, that describes the amount of work that's done by the recursive function. And the recursive equation that describes merge sort is this one that you see right here. Now, T of n in this equation represents the time it takes for this merge sort algorithm to sort a list of n elements. So that's what this Tn represents, the time it takes to sort a list of n elements using merge sort, of course. And that is equal to 2 times the time it takes to sort two lists of n over 2 elements. And then it takes n steps to combine these two sorted sublists, basically. So that's how you should understand what this equation represents, basically, where this 2 times t of n over 2 comes from, and then that n, which represents the amount of work that goes into merging those two sublists. All right. For simplicity, we will assume here that n, the size of the list, is a power of 2. N has the form 2 to the k for some k, right? And going back to your calculus course, you may recall this is an exponential equation, n equal to 2 to the k. And if you try to solve this equation for k, the answer will be k is equal to log base 2, which I haven't written the base here, log base 2 of n. So out of that equation, we know that k should be log base 2 of n. So again, reviewing, we'll assume n is a power of 2. That means that n has this form, 2 to the k, which means that k is log base 2 of n. Now, going back to the equation, this recurrence equation that we described oftentimes comes with an initial condition. And for us, the initial condition is that the time it takes for this algorithm to sort a list of one element, a list with one element, we are going to say this is equal to 1. Now, the method we use to solve this recurrence equation is by expansion. Now, what does that mean? What we do, we recursively or repeatedly, we keep expanding this term t of n over 2 using the original, this formula for the recurrence equation. Now, let's go through this. Now, based on this formula that I have here, right, what would t of n over 2 be? Before I get to that, let's study this formula in more detail. This is t of n. So look at the right-hand side. What happens to that n? Well, in the first term, n is divided by 2, and then you add that same n here. Right? This is n, the same argument as this n that you have there. Now, based on this formula, what would t of n over 2 be? Right? So the left-hand side, instead of t of n, I have it at t of n over 2. So based on this formula, it will be equal to 2 times t of n over 2, just that n, this n in the numerator right here, is now divided by 2. But here, instead of just n, I have n over 2. n over 2 divided by 2 will give me n over 4, right? And then this last term that you see here is exactly the same as the argument right there. So it's n over 2 remains as n over 2. So what I do, I go into the equation and expand this term. And once I expand it, what I come up with is this. T of n is equal to, there's that 2. T of n over 2 is expanded into 2t of n over 4 plus n over 2, plus that single n that you see in there. Next, we have to basically expand t of n over 4, right? That's the next level of basically recursion, which represents pictorially is represented by this. Now, how do I expand t of n over 4? There it is. What is t of n over 4? Again, going back to this formula, this means it's twice n over 8, dividing n over 4 by 2. That gives me n over 8 plus n over 4. So I go back to the equation and expand t of n over 4 by its expansion, basically. And this is the expression that I have. Now at this point, we'll try to simplify this expression. And algebraically, you'll notice that this expression simplifies to 2 times 2 times 2, which is 2 to the 3. T of n over 8, I can write it as n over 2 to the 3. 8 is 2 to the 3. Plus, what happens here, the 2 here, this 2, let me just get out of this equation, this 2 that you see here and this other 2 that you see here, both of them are multiplied into basically n over 4. So I have 2 to the 2 times n over 4, and then I have this basically outer 2, this 2 multiplied by n over 2, so I have 2 times n over 2, and this n sits right there. So in a way then, what you have here, this 2 to the 2 is 4, this 4 cancels that 4, so I have n plus 2's cancel out, I have another n plus n. So really, this pattern or expression is 2 to the 3 t of n over 2 to the 3 plus 3n. So all these 3 terms that you see here, really, it's equivalent to 3n. Now, the next question is, how far do I keep expanding, right? You basically need to identify a pattern based on what you see here, right? And it's kind of clear what the pattern is. So every time you expand, the next time it will be 2 to the 4 t of n over 2 to the 4 plus 4n. The one after that, it will be 2 to the 5 t of n over 2 to the 5 plus 5n. So again, the question is, how far do you expand? For that, you go back to the initial condition. You will expand until the expression, this expression that you see inside t, this argument inside t, reaches 1. And when would that reach 1? When I repeat this expansion k times, right? Because we assumed, the assumption was that n is a power of 2 and can be written as 2 to the k. We don't know what k is yet. Of course, it is log of n when you solve it. But we say that, again, we are going to expand this expression k times. So you are going to come up with t of n is equal to 2 to the k, t of n over 2 to the k plus k times n. And due to the this relationship between n and 2 to the k, that k will be equal to log base 2 of n, and the original expression, the expansion, will become this. T of n is equal to 2 to the k, t of n over 2 to the k plus k times n. That is equal to, now 2 to the k is n, so I'm going to replace that 2 to the k by n. And this t of n over 2 to the k, once again, we expanded it so that we reach 1, the initial condition. This is t of 1. And then plus, What is k times n? K, as I said, it's log base 2 of n. So this becomes n times log base 2 of n. Replacing this t of 1 by 1, right? So I have the final computation is n plus n log base 2 of n. And as we discussed in the class, when we use big O notation, we just enter the largest term in the expression. So between n and n log n, which one is larger? It is n log base 2 of n. So we say that this is big O of n log base 2 of n. So the merge sort algorithm is n log n type of an algorithm. If you recall, selection sort algorithm was quadratic. It was big O of n squared, right, which is slower than this one. N log n is better than n squared in terms of speed.